The Oort cloud is an immense and roughly spherical shell of small bodies that revolve around the sun at extreme distances. It's not exactly known how far away the Oort cloud might be, but estimates range up to more than 1,000 times the distance of Neptune. The Oort cloud begins past the Kuiper belt and extends beyond the influence of the sun's magnetic field. That technically brings it out into interstellar space. The Oort cloud is thought to be filled with frozen fragments of water, ammonia, and methane that were left over from the formation of the solar system. There could be billions or even trillions of objects, and some could be large enough to count as dwarf planets. Many long-period comets, that is, comets with an orbital period of longer than 200 years, are thought to come from the Oort cloud. It takes its name from Dutch astronomer Jan Oort, who proposed its existence as the source of such comets. Interestingly, the Oort cloud has never actually been observed. It's so far away that we can't send any probes to explore it, and its objects are so small and dark that we can't really see them. We can only observe them when something disturbs their orbits and sends them towards the sun. There are a few notable objects that may have originally come from the Oort cloud. First, there's Comet Hale-Bopp, which is a long-period comet that was visible for nearly a year and a half in the late 1990s. There's also Sedna, a dwarf planet that's thought to be about 3/4 the size of Pluto. It's known for its wildly elliptical orbit, which has led to speculation that it could be the innermost Oort cloud object known. And there's also Halley's Comet, which is probably the most famous comet of all. Halley's Comet is now a short-period one, but it may have originally come from the Oort cloud before gravitational influences shrank its orbit. Most long-period comets are only ever seen once because of the length of their orbits. Countless more have never been seen by humans, and there are others that have just never ventured close to the sun at all. Regardless, the Oort cloud is a very important piece of the solar system and its history, so let's take a closer look. The Oort cloud, as previously mentioned, is extremely far away. It's the most distant region in the solar system, technically in interstellar space, and its objects orbit at the very edge of the sun's gravitational influence. The inner edge of the Oort cloud is thought to lie around 2,000 to 5,000 astronomical units from the sun. The outer edge is much further away, potentially up to 200,000 astronomical units. To really put that into perspective, the Oort cloud could extend up to half the distance to the sun's nearest stellar neighbor, Proxima Centauri. From the Oort cloud, the sun probably just looks like an extremely bright star. It might take 10 to 28 days for sunlight to reach the inner edge of the Oort cloud, and up to a year and a half for it to travel past the outer edge. You know, Voyager 1, the first spacecraft to pass the heliopause and also the furthest man-made object from Earth? It won't enter the Oort cloud for 300 years, and it won't exit the other side of it for up to 30,000 more. That's just how far away this thing is. Objects in the Oort cloud don't travel around the sun in the same direction on a shared orbital plane like the planets do. There's a reason it's called the Oort cloud and not the Oort belt. The objects within it surround the sun in a very sparse shell. Most of these objects are smaller than 60 miles in diameter, and the total mass of the Oort cloud could be up to 100 times the mass of Earth. That might sound like a lot, and it definitely is, but Jupiter is 300 times the mass of Earth. Yet 99% of the solar system's mass is tied up in the sun, and 99% of what isn't is in Jupiter, so everything else seems kind of small in comparison. So the objects in the Oort cloud are super far away, but how did they get there? The leading theory is that they weren't always so far from the sun. After the sun and planets formed, there were a bunch of tiny chunks left over called planetesimals. These objects were scattered by the gravity of the planets. Well, I say the planets, but it was primarily Jupiter. If you ever have to ask, how did this thing get flung so far out there? The answer is probably Jupiter, and if it wasn't, then it was probably Neptune. Some of these planetesimals were ejected from the solar system entirely. Others were flung into eccentric orbits, still bound by the sun's gravity, just barely. These ones were far enough out that galactic influences also tugged on them. In fact, the strongest influence was probably the tidal force of the Milky Way galaxy itself. Besides being made up of planetesimals that were flung out by Jupiter, the Oort cloud could also capture objects that didn't form in the solar system. Because objects in the Oort cloud are right at the edge of the sun's gravity, the slightest external force can influence them, either sending them out into interstellar space or spiraling towards the sun. These forces can include the gravity of passing stars, interactions with dust clouds, or the galactic tide, the aforementioned tidal force of the Milky Way galaxy. At one point, some astronomers believed that a hypothetical gas giant within the Oort cloud could be disturbing it. This hypothetical planet, which was thought to be several times the mass of Jupiter, was given the name Tyche. However, its existence was ruled out by NASA's WISE mission, which collected no data showing the presence of such an object. In 1932, Estonian astronomer Ernst J. Opik suggested a possible distant reservoir of comets. See, comets eventually burn out as their close approaches to the sun exhaust their volatile gases, and because this happens relatively quickly, Opik argued there must be a reservoir that can constantly replenish the supply of comets, otherwise they all would have burned out a long time ago. Opik's idea was revived in 1950, when Dutch astronomer Jan Oort proposed the existence of the region that now bears his name. In addition to the burning out problem that Opik used, there were calculations that showed, in theory, Jupiter should eject all long-period comets over a relatively short time span. So Oort basically said, well, we still see these things, so they've got to be coming from somewhere. The problem is, by the time long-period comets are seen, their orbits have already been disturbed and they're no longer in the Oort cloud, and it can be hard to distinguish old ones from new ones. So Oort had to compute the original orbits of several comets, and in doing so, he showed that many of them came from about the same distance, and thus he showed the distant reservoir of comets must exist. Math is pretty impressive, isn't it? When it comes to space, if there's not enough direct observational evidence, sometimes the math alone is enough to prove something exists. And that's all I've got on the Oort cloud. This is a shorter one, I know, but that's alright. It's still very interesting. My original plan was to conclude Solar System Spotlight with this video. I figured it would be a fitting end to the series, you know, closing it out with the most distant region of the solar system. But I've changed my mind, and rather than ending Solar System Spotlight here, I actually have one more video that I want to make, and that will be the end of the series. I hope you enjoyed this video about the Oort cloud. It would be great if you could leave a like, and I would really appreciate it if you could subscribe if you want to see more. Thank you again for watching, I hope you have a good day, and I'll see you next time.